Hello, class. So today we are covering 10.4, the algebra of matrices. But before we get into the algebra of matrices, we're going to go ahead and do a little bit of 10.3, which introduces matrices. Okay. All right, so 10.3, you don't have a homework assignment for 10.3, so this is just strictly notes. That way 10.4 will make more sense. Okay, so 10.3, matrices and linear systems. Okay, so we're going into matrices, so you need to know what a matrix is. So it is a rectangular array of numbers with m rows and n columns. And I will draw an example for you. Okay, so here's an example. You could have something that looks like this, and you have these numbers: 2, -1, 3, 4, 0, 1. Okay, so this here is a matrix, and here 2, -1, 3 represents row 1. 4, 0, 1 represents row 2. Okay, and 2, 4, looking at it vertically, 2, 4 represents column 1. 0, -1 represents column 2. And this 1, 3, 3, 1 over here is column 3. Okay, so we see here that this matrix is made up of 2 rows and 3 columns. And so the dimension which is expressed by the number of rows by the number of columns, would be here we have 2 rows and 3 columns. Okay, so this matrix here is a 2 by 3 matrix. All right, so in general, you will have this matrix. It could be however big it wants to be. And this here, this element here would be in the first row and also in the first column. So here we say first row, first column. This next element, we say it's still in the first row, but now it's in the second column. This one here is still in the first row, but now it's in the third column. And this here is in the first row, fourth column. And we could keep going. So however far down we go, it's still going to be in the first row, but it'll be in the nth column. Okay, same thing with this next element over here. This one is in the second row, so we use a 2, and in the first column. This one here is in the second row, but the second column. And this one here, second row, third column, second row, fourth column. Keep on going. We're still in the second row, nth column. Okay, and we can keep doing that with the third row, fourth row, etc. But I think you get the picture. So let's just go down to the mth row, first column, row M, second column, row M, third column, row M, fourth column, and we can keep on going until we're down here, row M, column N. Okay, so here, the dimension, again, is your row by column. And so we have how many rows? We have M rows. And how many columns do we have? We have N columns. Okay. And here, if you have some element and it has these numbers, the I here represents the row. Okay. And the J here, this number, would represent the column. So where Aij is the number or element in the ith row, row I, and jth column. Okay, so for example, if I have this element and you see a 3 and a 5 here, then this tells me that it's, again, it's always row first and then column. So this tells me that A is the number in the third row and fifth column. Okay. All right. So last time we covered systems of equations and we looked at how to solve systems. We looked at substitution method, elimination method, graphing method, and then we looked at Gaussian elimination. So we're doing matrices now because matrices are just another way to solve systems of equations. Okay, so if we have this linear system, okay, suppose that I have this one here, 3x minus 2y plus z equals 5, and x plus 3y minus z equals 0, and let's have negative x plus 4z equals 11. We could easily translate this into what's called an augmented matrix. And from here, once we have this augmented matrix, we can do our solving by doing that Gaussian elimination on this matrix. Okay, so this augmented matrix would look like this. So I would take all of those coefficients, 3, negative 2, 1 in that first row, 3x minus 2y plus z. I would take the 3, the negative 2, and the 1. Oops, negative 2, 1. Okay, and then that second row, I would take the coefficients there, 1x plus 3y minus z. So that's 1, 3, negative 1. And then that last one, we're going to use the coefficients, negative 1, 0. There's no y there, so negative 1, 0, 4. Okay, so if we stop right here, this would just be a matrix, but we're going to have an augmented matrix. So here, I'm going to draw this line here. And in this column, I'm going to have the other side of the equation. So where we have the 5 over here where we have the 5, 0, 11, I'm going to put them right over here. Okay. All right, so 5, 0, and 11. So this here would be your augmented matrix, and we would try to do our row echelon, our Gaussian elimination to eliminate the 1, the -1, and the 0, get that triangular form. And when we get that triangular form, we use Gaussian elimination. We don't call it triangular form here. We call it row echelon form. Okay, so when we try to get these to all be 0, right? So that would be our triangular form. Okay, so here, triangular form. Can still be reached using Gaussian elimination. But instead of doing it on the system, you would do it in the augmented matrix, okay, which is just a different form of that linear system. Okay, and here we don't call it triangular form. We actually call so here it's called row echelon form. Okay, but again, we're not doing this here 10.3. We're going to be doing 10.4. Okay. But we will be in 10.6, we will revisit systems, how to solve systems using matrices. Okay, but this one, if you did the Gaussian elimination method in the last section, you can see that it's a little time consuming. And I think all of these, whenever you're solving a larger system than a X and Y, it's a little time consuming. Okay, but what's really cool about these, and the reason why we use matrices here to solve systems, is because we can actually enter a matrices into graphing calculators, some sort of computer, and it will do the row operations to get it in row echelon form. So it'll do all the Gaussian elimination and get it here and solve the system. Okay, so that's why this is sort of a nice method. Okay, so let's take a look at 10.4. So that was 10.3, a short little introduction to matrices. Okay, so in 10.4, we're going to be looking at the algebra of matrices. So we're going to be looking at addition, subtraction, the two types of multiplication. Okay. All right, so 10.4, the algebra of matrices. Okay, so let's start with equality of matrices. This one's pretty straightforward. The matrices A and B are equal. If and only if, and we use that symbol, IFF, if and only if. You can spell it out if you want to, or you can use that symbol. If and only if they have the same dimensions which makes sense. And corresponding entries are equal. Okay, so we'll look at some examples and try to determine whether or not they're equal. Okay, so let's take a look. Suppose I have, okay, so let's do this one. Suppose matrix A is 1, 3, 5, 2, and matrix B is 1, 3, 5, 2. Okay, so that's kind of obvious. They have the same dimensions and they have the same entries. So yes, matrix A equals matrix B. Okay, let's take a look at this next one. Suppose matrix A is 3, negative 2, 1, 0, 5, negative 4. And suppose matrix B is 12 fourths, negative 28, 14, 1, 0, 10 over 2, negative 4. Okay, so at first glance, it might look like they are not, but if you reduce those fractions in matrix B, 12 over 4 is 3, negative 28 over 14 is negative 2, 10 over 2 is 5. So here, all of the entries match. So A does equal B. Okay, let's take a look at this one. Suppose matrix A is 1, 2, 3, 4. And suppose matrix B is 1, 2, 0, 3, 4, 1. Okay, so first of all, they're not even the same dimension. One is 2 rows, 2 columns. And matrix B is 2 rows, 3 columns. So here, matrix A is not equal to matrix B. Okay. And let's take a look at one more here. If A is 2, 1, negative 3, negative 4. And suppose matrix B is 2, 1, negative 3, 8. Okay, so they have the same dimension. They almost have the same elements, but the negative 4 and the 8 don't match up. So here, A is not equal to B. Okay. All right, so those are equivalent matrices. Let's take a look at some operations with matrices. All right, so we're going to go ahead and take a look at addition and subtraction. All right, let's take a look at this first example here. Suppose that I am going to add these two matrices together, negative 3, 5, 1, negative 2. And I'm going to add that with this matrix, 7, negative 1, 3, negative 2. Okay, so here, all you do is add the corresponding entries. So you add negative 3 here, this entry, right? First row, first column, with this one here, 7, first row, first column. Then you would add the 5, first row, second column, with first row, second column. Okay, you add this one with the 3, the negative 2 with the negative 2. Okay, so clearly here they have to have the same dimensions in order for you to add or subtract them. Okay, so just add, subtract corresponding entries. Okay, so the negative 3 with the 7, that'll give me 4. 5 plus negative 1. And then down below, 1 plus 3. And negative 2 plus negative 2. Okay, so that's what we would get. Okay, same thing with subtraction. So let's take a look here. Suppose that I have this one here, negative 3, 5, 1, negative 2. And now we're going to subtract 7, negative 1, 3, negative 2. Okay, why don't you go ahead and try this one, hit the pause button and give it a go, and then come back and check your answer with mine. Okay, so you should have added negative 3, or combined negative 3 minus 7, it's negative 10, 5 minus negative 1, so that becomes plus 1, so that's 6. 1 minus 3, negative 2. Negative 2 minus negative 2, and we get 0. Okay. All right, let's see. Scalar multiplication. So we have two kinds of multiplication when we're dealing with matrices. We can multiply by a scalar, like a real number. So we can take this matrix here and multiply it by 2. Okay. And then we also have matrix multiplication, where we multiply this matrix together with, say, that matrix. Okay. So we'll take a look at both of them, but right now, we'll end this lesson with matrix multiplication, but for now we're going to stick to scalar multiplication and then some properties and some solving, and then we'll look at matrix multiplication, which might seem a little strange at first. Okay, so let's take a look. Scalar multiplication, multiplying by just a real number. So this one will be intuitive. Okay. So what this means is just multiplying a matrix by a real number as opposed to another matrix. Okay. All right. So for example, suppose that I have this matrix, 1, negative 3, negative 4, 2. And suppose I'm going to take this matrix and multiply it by 2. Okay, so all you have to do here is multiply all of the entries inside the matrix, 1, negative 3, negative 4, and 2. Multiply all 4 of those entries by 2. So we get 2 times 1 is 2. 2 times negative 3, negative 6. 2 times negative 4, negative 8. And 2 times 2, which is 4. Okay? So that's scalar multiplication. All right, let's take a look at this one here. Let's make it a little more exciting. Let's let matrix A equal 2, negative 3, 0, 5, 7, negative 1. And let's let matrix B equal 1, 0, negative 3, 1, 2, 2. Okay. And suppose you have to find 5 times A minus 2 times B. Okay, so that's a little more interesting than the above example. All right, so let's go ahead and do that. 5 times A minus 2 times B. So that means we're going to do 5 times 2, negative 3, 0, 5, 7, negative 1, minus 2 times 1, 0, negative 3, 1, 2, 2. Okay. All right, so let's go ahead and multiply all the entries here by 5. So we get 10, negative 15, 0, 25, 35, and negative 5. Okay. And then here I'm going to multiply all the entries by negative 2. So I'll just change that to addition. So we get negative 2, 0, 6, negative 2, negative 4, negative 4. Okay. And then now here we can go ahead and add the entries 10 and negative 2. Okay, this is starting to slow down. Okay, 10 and negative 2, 8. Negative 15 and 0. Negative 15. 0 and 6. 25 minus 2. 35 minus 4. Negative 5 and negative 4. Okay. So that makes it a little more interesting, but not complicated. Okay, so let's take a look at some properties. Okay, so we looked at addition, subtraction, and scalar multiplication. So let's take a look at some properties here. Okay, there we go. All right, so let A, B, and C be n by n matrices. Okay, and the lowercase c and d be scalars, real numbers. Okay, so then we have the following properties. Okay, so A plus B, matrix A plus matrix B will equal to matrix B plus matrix A. Okay, so here it's commutative. So we have the commutative property for matrix addition. As opposed to like scalar addition. Okay. And then we also have this one. This might look familiar. A plus B. If you add these two matrices first and then add this matrix, you'll get the same answer if you add these two matrices first, B and C, and then add matrix A. Okay, so you've seen this property before. It's called the associative property. And this is for adding matrices, so matrix addition. Okay, and then we also have this one here. If you do little c, okay, so this is a little c. You know what? I should just, never mind. Okay, so if you do the scalar, okay, so if you do this little c times lowercase d, capital A. That's going to be the same if you do C times D first, okay? And then multiply the matrix. Okay, so we have associative property with the matrix, and then we also have associative property here. Associative property for scalar multiplication. Okay, as opposed to matrix multiplication, which we haven't done yet. Okay, and then this one over here, last one, we have the distributive property. And of course, that's going to be for scalar multiplication. Okay, so if you have these two scalars, lowercase c plus lowercase d times matrix A, that's going to equal lowercase c times A plus lowercase d times A. And whether you have, if you have two scalars inside the parentheses multiplied by a matrix, or if you have two matrices inside inside the parentheses, and you have a scalar here. I'll use D. Okay, so you'll still get A times D plus B times D. Okay, so we have the distributive property. And again, this is for scalar. Scalar multiplication as opposed to matrix multiplication, which is coming up pretty soon. Okay, so let's take a look at solving matrix equations. Okay. All right, so let's take a look at this example. Let's solve for matrix X. Solve for matrix X. Okay, so we know X is a matrix, not a scalar, not a real number. Okay. Okay, so solve for matrix X if A, matrix A, equals this matrix, 2, 3, negative 5, 1. And matrix B equals this matrix, 4, negative 1, 1, 3. Okay, and here is your equation. Okay, and 2x minus A equals B. So remember, X is a matrix. Okay, all right, so I'm going to go ahead and bring that equation down here. 2x minus A equals B. And we go ahead and solve for x as usual in this equation. As usual. All right, so I'm going to add A to both sides. And then I'm going to multiply by 1/2 on both sides. And so this is going to be addition of matrices A and B, followed by scalar multiplication 1/2. Okay. All right. So now that we have it written out for x, now I'm going to substitute my matrices for b and a. Okay. So x is equal to 1/2. Here, let me write that down. Substitute matrices for a and b. Okay, so now I'm going to have 1/2 times, okay, matrix B. I need to scroll up. Let's see what it looks like. Matrix B is 4, -1, 1, 3. Plus matrix A. Matrix A is, if I look up here, scroll. There we go. Matrix A is 2, 3, -5, 1. Okay, so I'm going to do everything inside the parentheses first. So I'm going to go ahead and I'm going to add those two matrices together. So 4 plus 2, 6. -1 plus 3, 2. -5 plus 1 is -4. 3 plus 1 is 4. Okay, so I have this here when I add those two matrices. And now I can multiply every element in there by 1/2. Okay, half of 6 is 3. Half of 2 is 1. Half of -4 is -2. Half of 4 is 2. So this would be our answer for x. So x would equal the matrix 3, 1, -2, 2. Okay. All right. Okay, so that's scalar multiplication, multiplying by that 1/2. So let's go ahead and take a look at matrix multiplication. So this is the one that's a little not so intuitive. All right. So first of all, you can only multiply matrices A and times B like this. If number of columns of A, matrix A, equals number of rows of B. Okay, so let's take a look here. So if I have, so here, let me just kind of give you a visual here. Okay, so if I have this matrix A, right? And suppose that my matrix A over here, okay, so suppose my matrix A here is an m by n matrix, right? Okay, so the columns of A, which is this letter n, right? So this one here has to match. So if I'm doing this times this, okay, so if I'm doing that multiplication, then the columns for A, which is n, have to match the rows of B. So here, this has to be an n by whatever else, okay? So those two numbers have to match. These two right here need to match, okay? If they don't match, you can't do the multiplication, okay? They need to match. Okay. And do you see this here? Let me see if I can grab. Okay. Do you see this here? And this here? Okay. So the M and the K right there, your answer. Let me go back to my pen. Okay. So this here will be some matrix C. Okay. And the dimensions of this are going to be, it turns out, it's going to be an M. Oh, that doesn't work out very well. Okay, you know what? Let me erase that. Okay. All right, so that is going to be an M by K matrix. Okay. So when you're multiplying matrices, you can only multiply them if those two inside numbers match. Okay. The columns of A, or your first matrix, the columns of your first matrix need to match the rows of your second matrix. Okay. And if they do, you can go ahead and multiply them, and you'll end up with a matrix. And the dimension of your answer is going to be M by K. All right. Okay, so let's take a look. Now for the tricky part. Okay, so over here, suppose that A, matrix A is 1, 3, negative 1, 0. And suppose that matrix B is negative 1, 5, 2, 0, 4, 7. Okay, so unlike addition and subtraction, where they have to be the same dimension in order for you to add them or subtract them, that's not true here. Okay, so that's not true here. So let's find A times B if possible. So first of all, let's check to see if it is possible. So let's see if the columns for A match the rows for B. So let's get their dimensions. So A is a 2 by 2. B is 2 rows, 3 columns. Okay, so we see that we do have a match. Okay, so here they do match. So yes, it's possible. We can multiply these. So they don't have to have the same dimensions. They just have to have the columns in A need to match the rows in B, and they do. Okay, and what happens is we're going to end up with a 2 by 3 for our answer. Okay. Okay, so we're going to end up with 2 rows, 3 columns. So 2 rows, so we'll get an element here, here, here. So we need to find out those We end up with a 2 by 3. So 2 rows and 3 columns. Okay, so question is, how do we find these elements? Okay, so this is kind of hard to show in this format here. It's a little bit easier if I were in class. Okay, so what you're going to do is you're going to take the row here and the column here. Okay, so you're going to do this row, this column. Okay, see how we have two elements here, 1 and 3? And you see how we have two elements here, -1 and 0? Okay, that's kind of why they need to match. That's why the columns here have to match the rows. Okay, so, and they do. We have 2 here and 2 here. And what we're going to be doing is to find this here, we're going to use the first row and the first column. Okay, and what we do is, because we have 2 elements here and we have 2 elements here, we're going to multiply corresponding elements. So this one, 1, and the -1. I'm going to multiply the 3 and the 0, and then I'm going to add those answers. You should be able to do it in your head. Okay, so you shouldn't have to use scratch paper or anything. So this first element with this first element, the second element with the second element, and that will give me my answer here. Okay, so 1 times -1, that's -1. Hold that in your head. 3 times 0, that's 0. And go ahead and combine those answers in your head. So that's -1 and 0. -1 and 0 is -1. So that's how you get that one. Okay. To get this, okay, so this is our first row, second column. Okay, so that means I'm going to use my first row, but I'm going to use the second column over here. Okay, this is first row, second column. So I'm going to use the first row, and I'm going to use second column. And again, when I look here in this first row, I have 2 elements. When I look at the second column, I also have 2 elements. Okay, so I do the 1 times the 5. Hold that answer in your head. 1 times 5 is 5. 3 times 4, that's 12. So 1 times 5 is 5. 3 times 4 is 12. So 5 and 12 is 17. So that's my answer over here. Okay? So let's go to the next one. I'm still in the first row, but now I'm in the third column. So I'm going to use my first row over here and my third column over here. Okay? Because this is in the first row, third column. So I'll use my first row and my way over here, my third column. Okay, again, 2 elements here, 2 elements here. So 1 times 2, combine that with 3 times 7. 1 times 2 is 2, 3 times 7 is 21. So we get 23. Okay, so I'm done with my first row. Since I'm done with my first row, I no longer need to use this first row. I need to come up with my second row. So then now I'm going to use my second row. Okay, so I'm going to use my second row right here. Okay, I need to find the second row, first column. So I'm going to use the second row, first column. Again, there are 2 elements here. There are 2 elements here. Let's multiply the first element with the first element, second element with the second element. Okay, so -1 times -1 is +1. 0 times 0 is 0. Add those 2 answers, +1 and 0, and we get 1. Okay, and then we do the same thing over here. I am in the second row, second column. So I will use the second row this one, and my second column, this one. Okay, 2 elements here, 2 elements here. So -1 times 5 is -5. 0 times 4 is 0, so -5. Okay. Now I'm down to the last one. Again, this is my second row, third column. So I'm going to use my second row and my third column. Oops. Okay. Second row, third column. 2 elements here, 2 elements here. -1 times 2 is -2. 0 times 7 is 0. -2 and 0 is -2. Okay, so that's how we find the elements when you do matrix multiplication. So you can see here, matrix multiplication is much more complex than scalar multiplication. Okay, but what's also interesting here is we talked about those properties and we said, oh, it's commutative. We said scalar multiplication, multiplying by a real number, is commutative. So that if I did 2 times matrix A, that's fine. That's the same thing as doing matrix A times 2. But if we take a look here and we look at matrix multiplication, not scalar multiplication, but matrix multiplication, we see here that if I try to switch these around and I try to do B times A, well, if I look at B, B is a 2 by 3, right? And A is a 2 by 2. We see that here, these inside numbers right here, these don't match. We have 3 and a 2. They do not match, so we cannot do this multiplication B times A. So we see here matrix multiplication is not commutative. Okay, so that's something to kind of notice. All right, I'm going to have you try one because, like I said, this is not very intuitive. So let's go ahead and have you try this one. Okay, so go ahead and try this one. A equals 2, -5, 0, 7. Matrix B, it is 3, 1, 2, -1. Okay, find A times B. Okay, all right. So if you try to find A times B, here, let's kind of set it up together. So let's see if it's even possible. So this is a 2 by 2. This is a 2 by 2. These here match. Okay, these here match. So yes, we can do this multiplication. And you should see that you should end up with this one over here. You'll end up with a 2 by 2. Okay? So I like to draw my matrix and have those blank lines so I know how many elements I'm trying to find. Okay, so we should end up with a 2 by 2, right? So 1, 2, 3, 4. Okay, so you'll need to find these 4 elements. Okay, so go ahead and hit the pause button and try to see if you can find these 4 elements. Okay, so I'm going to take this first row and this first column to find this element here, which is in the first row, first column. Okay, so to find this, I need to do first row, first column. Okay, so 2 times 3 is 6. Negative 5 times 2 is negative 10. 6 and negative 10 is negative 4. Okay. Now this one, I'm still in the first row, so I'm still going to use the 2, negative 5. But now I'm in the second column, so now I'm going to use this column. So 2 times 1 is 2. Negative 5 times negative 1 is 5. So 2 and 5 is 7. Okay, now I'm over here. Okay, so right here, I am in the second row. So now I'm going to be using the second row. Okay, I'm going to find the one in the second row first column. So I'll be using my first column. So 0 times 3 is 7 times 2. So that's going to give me 14. Okay. And this last element over here is in the second row. So I'll be using 0, 7. And the second column, so I'll be using 1, negative 1. Okay. 0 times 1 is 0. 7 times negative 1 is negative 7. Okay. So these are the 4 elements you should have gotten. Okay. All right. Let's go ahead and try one more. If you feel like you need to try one more, try this one. If you think you're done, you get it, then you can just go ahead and stop, okay? Because I'm going to end with this last example. All right, so let's go ahead and try this one. Suppose matrix D is 3, 2, negative 1, 1. Matrix E is 2, negative 1, 0. 3, 1, negative 2. And suppose you have to find D times E. All right, so first of all, let's just check together to see if this is possible. Actually, you do all the checks too. So go ahead and hit the pause button and see if it checks out, if you're able to do this, and figure out what size matrix your answer will be. Okay, hit the pause button. Okay, so you should end up with a 2 by 3. All right, so I'm going to use this first row, first column. 3 times 2 is 6. 2 times 3 is 6. So we get 12. Next column, still on the first row. Second column. 3 times negative 1 is negative 3. 2 times 1 is 2. Negative 3 plus 2 is negative 1. Still in the first row, third column. So first row, third column. 3 times 0 is 0. 2 times negative 2 is negative 4. Okay, now I'm on my second row. So now I can start using the negative 1, 1. Negative 1 times 2 is negative 2. 1 times 3 is 3. 3 and negative 2 is 1. Next column. -1 times -1 is 1. 1 times 1 is 1. So we get 2. Third column. So I'm still using -1, 1, but I'm going to use it with this third column. -1 times 0, 0. 1 times -2 is -2. 0 and -2 is -2. Okay, so that's how you do your matrix multiplication. Okay, if you have any questions, make sure you message me on the Remind app or you email me. You'll get a quicker response from me if you use the Remind app. All right, you guys have a good rest of your day or night.